Hello. Wow. Nice buying a set. Hello. Hello everyone. We are back with the 30 Days Lost in Space franchise. Very excited to continue on with this. We have got 2 days, count them 2 days left worth of content from this kit. Today is day 28, where we work with the landing gear. So we're going to see what this entails. I do know it's going to build off of what we've already previously set up. Looks like they're going for like a grand finale and we're hooking a bunch of stuff up at once, which is why in the previous iteration where we hooked up what did we hook up to the analog lines? We hooked up the switches. We hooked up the dip switches to the analog inputs / outputs, because for today we're going to be hooking up the keypad again, and that's going to integrate into the rest of the project. So we can use analog pins as digital ones, which is super cool because up until the last go around, that was not something I knew. So super cool to see that we're continuing to build on the knowledge that is this learning kit. And with that, we're gonna hop right into it. Now I say that, not knowing why I'm seeing nothing on the screen. I gotta have to restart. I don't know if I've experienced hardware failure or something else, but my other camera just went out, so pretty sure they share the same data bus. So stream is going to stop because I have to reboot this machine. I will be back momentarily. I apologize. I didn't anticipate this, as you can clearly see. I'm a little broken at the moment, as I no longer have tracking. I have hands, but I have no head. So give me a couple minutes. I'm gonna restart. Yay! Surprise! It's a toaster. I'm back. Thank you for waiting. Okay, so I'm really mad at myself. I found the problem and I'm stupid. I had one of these moments because I was reseating the wrong cable, which is why I lost my tracking. I mixed up with which black wire out of all the black wires was the one for the capture card that was loose. So that's fine now. It's not loose anymore. I'm a little sad, but we can proceed now. Thunder, I'm so mad. Like, why is every product that's sold always the same color? All the cables are the same color. It's this aesthetic. You gotta give me a couple minutes. I gotta get everything signed back in. Oh, hang on. I have no closed captioning. I forgot to launch the closed captioner service, amongst other things. Bear with me as I sign in to everything once again. Oh, I suppose it is. I can admit it makes a brother sad, though, when you have to sign back into everything. Alright. Boop. Click button, get my mortgage. There we go. Alright, I got captioning again. And I'm gonna click the button over here. And click some buttons over here. And through the patience that is the toaster, we're almost back. I was about to dread the fact that I thought my capture card died. Because it was blinking red and then just shutting off, which usually indicates not enough power or hardware failure. There isn't much in between. So I'm like, oh no. I'm like, but I haven't changed anything. That's not good. Turns out I'm silly. Facility is a lot cheaper than dead hardware. Thank you, Pine. This is appreciated. Alright, go back over here. And I'm gonna go over here. And we'll go over here. Ah! Alright, cool. So now I can pump the brakes on that, come back over here, and I get to click on that one. Alright, that's better. I actually get to be in frame. Hello. I'm so sad. That's okay though. It was a good amount of troubleshooting. This is what we do, okay? We'll make it work, okay? Unfortunately, I know why that wire came loose because of where it's positioned in this room. Oh, hey, I gotta grab my water. That meandered to the other side of the room. It's funny too, because I did actually knock over my water, and it fell onto my floor, but thankfully the cap didn't pop, so I didn't end up dumping a bottle of water on my floor. Which I commit I'm pretty happy about, because that would have stunk to have to clean up. Okay, excellent. Now all the noise is out of the way. I think my message unpinned itself. Yeah, because I restarted stream. Okay, alright, good. Alright, we're going to proceed in an orderly fashion, I hope. Let's see here. That one. Do that one. Alright, cool. Let's see what on earth we're getting ourselves into here.
Good morning, stellar traveler.
Hello.
As the gentle hum of our ship fills the void around us, we find ourselves at the
Who needs
precipice of a
landing gear?
momentous task.
Guys.
Can you feel the anticipation?
Sure can.
Just 48 hours away from the mothership, and we're ramping up for our final challenge,
That's
repairing the docking gear.
Okay.
This isn't just any repair. It's a symphony of all we've learned, all the tools we've acquainted ourselves with, converging for one grand purpose. Let's ensure that when we touch down, we do so with more grace than a dying star. The horizon of home beckons, and we have much to do. Today's task...
Okay, I have to pause this because the idea of the grace of a dying star goes one of two ways. Some of you might know what that means. Either you go out like a white dwarf and there's not much sound, or you go out like a red giant and go supernova and burn everything in your path. I don't know if either is really more ideal over the other, but oh knows.
Explorer is both intricate and comprehensive. Remember the code from our previous day's adventure? We'll need
Perhaps.
that, along with the symphony of our passive buzzer and the visual allure of our OLED.
Do
And,
we now?
don't forget the 4x4 keypad, which will serve as the bridge between our will and the majestic mechanism of our landing gear. Yesterday, we ensured our dip switches are safety compliant. So, once all three are flipped,
They're
that
very
very
dippy,
keypad will
quite
be our
switchy.
instrument
I like
to
it.
both deploy and retract our landing system.
Mm-hmm.
The rest of our tools will come center stage tomorrow. Let's glide through this with the precision of a starship pilot, shall we? Let's move on to how we're actually going to code this. We need a way to figure out if we have flipped all three of the dip switches and passed our necessary safety checks. We can probably do this by checking all of the switches' states and only continuing once they've been activated. Next, we need to add today's additional logic for our 4x4 keypad. We will be using that to deploy our landing gear. It doesn't necessarily matter which button makes it deploy, so let's just use A. That should work. Let's review the cached instructional material from your mission resources and give it a quick test.
What does this do? Clicks button.
Hello, everybody, and welcome back to day.
Hi, Alex. Bye, Alex. Yes, I do enjoy the fact that any random button could deploy the gear that makes the ship stand on its own. Glad to see that doesn't seem to matter too terribly much. That's okay. Alright. We're gonna do stuff and things in a reasonable fashion. Right, exactly. Okay, so to pick up where we left off from last time, the rest of this diagram is the same except for the 4x4 keypad. Uh-oh. It's fine, it comes out in the wash eventually. 4x4 keypad we're going to attach to the digital lines here on the side of our board. I am going to plug back in the what we did from last time, just so we could see it before we modify it. Alright, cool. It looks like my angle's off. You know, I would like it if things could stay somewhat not busted. Straighten that out a little bit. There we go. Alright. Now we're back in frame, and then let me get us a little closer so we can see what we're up to here. Going to zoom in. I said zoom in. I had the wrong camera. Did I have the wrong button selected? Nope, I was pretty confident it was this one. Oh. Alright, I'll do it manually. That's fine. I got a lot of the stuff to behave. Supposedly not all of it. Why are you blinking at me? That's probably not a good color. Is the remote not plugged in? Good question. Where does the remote plug in? No, it plugs in over here. When in doubt, unplug it and plug it in again. I'm telling you, it seems to be that kind of stream, apparently. I'm not even really sure what the remote's doing now. It is blinking quite a few different colors. So I'm going to just turn that off, turn that back on, and then I'm going to put the little battery cover back on, and I'm going to, yes, in true fantastic IT fashion, I turned it off and back on again by removing the batteries from the remote. Okay, let's try this again. All right, what was I doing? I was doing things and stuff. I am attempting to do my thing, and my hardware does not want me to be doing that today, apparently. Okay, let's get this plugged in and get going here, because I would like to finish this at some point in the next decade. All right, so we have got, because we're a lot of the hardware is going to stay the same, but what we have is going to look a little different. That's why I want to bring this up so we can do a little comparison. It's what makes it fun. I mean, to an extent, you're not wrong. Okay, we got a couple things going on here. So our board and its wiring is going to stay the same, except we're going to add on the keypad that's going to tie in here, right? We then have a graphic of the dip switches, and then we have their actual positioning down here, and then our 7-segment display that then allows us to count. So that was all on, right? And 0 is all off. This is a binary counter, right? Because if I turn on the first switch, which is a little hard to do here, I get 1, and then that respective switch in the animation changes, and it flips up, and then the other two stay off, right? And then to go to 2, I have to turn on the center here, like so, because we've got 1, 2, and 4. We go to 3. We will then turn on our first position, which gets us 3, and then those first 2 are on. And then to go to 4, turn off those, flip on the far left, we get a 4, and then we can finish cycling through by getting 5, and then doing 6 and 7, which 6 is in there, but that's just another one of the configurations. So this is what we had set up from last time in the go around here. Howdy, Porsche. Welcome on in. But what we're going to do today is we're going to add our 4x4 keypad into the mix so that we can click buttons and be able to control our landing gear. Now, the example that they mentioned is that the letter A is going to be the one that is going to control the gear going up or down, which it'll show us further down, I believe, which one of these is A. Because I want to say that it was 1, 2, 3A. I want to say it was S4 was the letter A, but we'll find out. It'll tell us which button we're supposed to click. So let me disconnect that from the computer. And then we're going to get this wired up, and then we will continue onwards with the exercise. I'm going to zoom the camera out a little bit so that we could see a little bit more of what I'm up to over here. And then I'm going to grab some jumpers, and I'm going to take a look here. So it looks like I am wiring this to pins 6 through 13 is what we're going to hook this up to. So the type of jumper we're going to use is going to be male on one side, female on the other, just like that, so that the jumper will push right onto the studs that stand straight up and down on our board here. So give me a moment while I get us sorted in fantastic fashion. Gonna get all these lovely colors on here. And with it being 8 little wires, that's a lot of little guys to stick in. Yeah, those, and then these. Okay, so I got them pushed on like that, and then that just makes this whole thing its own harness now. Now, not all these have been separated, but if they have been in the past, that's why some of these are in like smaller sections from just, you know, toying around and doing other things with this. So I need to pay attention to which way the board is oriented here. So it gets plugged in this way. So this is the top wire, which is going to be in 13, and then everything else below it. So I now need to orient this in a way I can actually plug this in, which is going to be entertaining, I'm sure. Forget to color code it rainbow. Yes, exactly. Rainbows. You're on to something. Alright, I got purple and blue. So purple is the first, or the top wire, which is going into 13, which will be right below ground. So I'm going to pop. This is going to be a nightmare to do while I'm standing. It's okay. I can handle the tiny wires. It's just seating everything is going to take a little bit of patience. But that's okay. So the one thing that's nice about being able to breadboard is that I can move things around. And if it doesn't really work out, that's okay. You can try again by moving some more things around as needed. Which does come in handy, but that also is a little bit of a double-edged sword, because you have to be careful that if you are plugging and unplugging, that you put stuff where it's actually supposed to be. And not reboot your webcam when your capture card's now. That's, I feel like that kind of goes without saying, but you know, it's what it is. Alright, so I got red and orange mixed on the lineup here. I got red and orange. I might be able to put these in together, like so. And the last two are yellow and green. Okay. We got yellow and green. Yellow is gonna go there. Green is gonna go there. Alright, cool. So now I have the board wired into the buttons, and
Whether we're going to use all the buttons or not, we'll have to see. But as of right now, wiring wise, they're all accessible, all 16. And then I can pop our friendly neighborhood board back into the computer. At this time, these buttons do nothing. So I can click stuff on here and nothing is going to happen. Because our dip switches are what make up our program for the time being. So I'm going to set those on off position, and then we're going to get the project code up, and then we're going to wander through the exercise. Oh yeah, actually wish you did breadboard stuff in school. I mean, it's such a fun thing to do.
It's something that, I mean, frankly, I always loved, but it wasn't until I started doing this that, like, even I got to have any of this kind of fun. I always used to get my hands on different pieces, but, like, never, like, the full beginning to end of just doing this. So I figured, the heck with it, let's go, you know? Which is how we kind of ended up where we are. I have 2 word tags. I do right now. I do! Fancy that! I'm amazed it let me do that. Was one of them uppercase? Ha! Well, now there's only one. Thank you for correcting that. Or noticing that, rather. I'm amazed it let me have duplicates. That's interesting. Miniature Tesla tower in servers. Ah, yes. The Tesla towers. Those are a lot of fun to play with. But very, very incredibly high voltage. They make some pretty scary sounds if you don't like the sounds of electricity. They are more or less harmless when used correctly, but they're terrifying to actually listen to. Okay. Alright, so now we got that going. We are going to start a new project. Now, we are building on what we did before, but because it's a new day, we're just going to bring over the code and build it in. Because as we toy with it, I'd rather them stay separate anyway. Okay, and then we're also going to have a new tab, and this one's going to have to be the name of the bitmaps, because we are doing separate bitmap files below the main code. And then this one's going to be called landing gear bitmaps, and don't forget the H. As such, or bad things will happen. Now, when I do that, it creates a separate file inside of the folder that we're working with. Even though it's going to upload the sketch in full to the board, we'll see here that there's the main sketch, day 28, which is an INO file. And then the H file is our helper file to make it so that the bitmaps that make up the pretty images we see on the OLED display, which would look like little dip switches, or the flip switches on the display, it puts it in a separate area because bitmaps take up a lot of coding space to make up the image. So to visually clean it up, we put it in a separate file and then just call upon it so that it's easier to read our code. So first things first, we're going to bring this stuff over. Now these are the different images that are going to make up our animation. Because what is an animation but a couple of still frames rapidly switched between, right? Pretty sure I can verify this. Yeah, I can verify that. All right, good. All right, so now that we have our helper file all stood up, now we're going to pull over the code that is responsible for the main project. And then we're going to wander through it. And since these exercises have gotten a little bit more on the complicated side, I'm no longer copying it in chunks. I'm just kind of pulling it over in one shot, which just makes it easier for me to not get lost. And as long as everything's linked and named correctly, this should verify. And then we'll jump into it. Yeah, calling a different file works as long as the route is completely correct. God forbid a small typo. Oh god, yeah. You are absolutely correct on that. You're missing something, whether that be a character, a period, an underscore, a space. Don't put spaces in file names. Please, for the love of God, don't do it. It did happen last time. I didn't include the H last time, or the period H. And even though it was there, it was not happy with me because I didn't give it the full file name. Now granted, I wasn't sure if the .h was implied or if it was required. Turns out it was required. Which is fun. But to be honest, I wasn't sure how the include was going to be, which is why we looked. The full legal name, right? Yeah, that's exactly how it be. Okay, so this is what we've got wired up now. We have our developmental board here, and then we have our 7-segment display tied into pins 2 and 3. Our clocking pin is pin number 3, which is a PWM pin, which stands for pulse width modulation. And if we take a look here, there's a little tilde next to this. It's very hard to see on camera. It's very, very small. But that indicates that that's a pulse width modulation pin. And then below it is our data pin, which is pin number 2, which then feeds the information that the display needs. Our wires for our 16 buttons comes across 8 wires. And the reason for that is that each button needs the signal and the return back to ground to be able to complete the button click. So every button has got 2 wires that are involved. Now what I find interesting is that our buttons, I don't think there's anything on the back of this. It's just a raw button. Let's see if I can reach that to check the back. Yeah, it's just solder joints on the bottom. There's no resistors on that. It's just a straight button board that then gets tied into that I/O header. Which is interesting because if we take a look down here at these dip switches that we have in the middle of the project, we end up sending 5 volts of raw power down one side, and then we sync the remaining voltage to the ground on the other side of the switch and then get a reading over here on whether it's engaged or disengaged. But when it's a button hooked up between 2 different leads, that allows us to gather that information without the additional resistors or feeding power. We could just read it directly from the pins, which is interesting in the way that that functions. And then the rest of this is the same: power wires and grounding. And then our OLED display is hooked up to our analog. The only thing that's a little different that I know I mentioned already like 3 times now is that our switches are plugged into the analog, and that's because our buttons are on the digital pins. Even though we were able to cheat and use the analog inputs for the switches, it didn't have me use some of these on analog, which makes me think that for the push buttons, you probably can't do that. I'd be curious to see what components are and are not allowed to play on the analog side. But for something as simple as just reading voltages, I could see how you can get away with that. But yeah, okay, so that's enough of the wiring diagram. Let us dig into the code. So first things first, we're going to take forever to scroll back to the top here. I'm going to swing over to our bitmap file for a quick second. And what we're going to see here is the name of our different bitmaps. We've got our landing 1, and then we've got landing 2, landing 3, landing 4. So we've got 4 frames that animate the landing gear animation that we're going to have on our screen. And they're just simply labeled landing underscore 1 through 4. And then we could see here, that's the size of it. It commented out, so it's 98 by 44 pixels, which means it does not take up the entire display. The entire display is 128 by 64. So this is only going to use a portion of our display, and that'll make sense because of the extra stuff we're going to have on our screen. So, as every project includes, we're going to include the Arduino suite. It is assumed if you don't load that you're using it because we're using the Arduino IDE, but it is good practice to include it anyway. Big difference. If you were to open this project in a IDE that is not the Arduino one, then you can do that, but you must have this include, or the compiler doesn't know you're using the Arduino suite, which is the hardware board we're playing with. And then we've seen it before. We've got the U8G2 library and the I2C communication wire protocol, which allows us to interact with the OLED display, and that allows us to communicate with it. Let's see here, and then we make our object to play with the Lander display, which is our OLED display. Let's see here, the comments say use 2 version of constructor in first page, next page for the OLED graphics to save memory. _2_ version of constructor in first page, next page for the OLED. Alright, yesterday we showed a way to move our large bitmap declarations so that our setup and loop code was near the top of our sketch using the forward declarations. However, it turns out there's a simpler way, and we've seen it used many times in the past. We can simply move our declarations into one or more include files, and then include them at the top of our sketch before we reference them. To create a new file, we do the things that we just did. And then that include is the file that exists in the same folder as the project. You must have all of your files for the project within the root folder of the project. If I moved it outside of the folder named date-28, then it won't be able to find it, and even if I gave it the full path, it won't find it because it has to be in the same folder. I don't know if that's a limitation of the IDE that we're using, or what that seems to be, but we don't give any Windows paths here. This is all very literal. Which is why you'll notice that it's just in quotes in the name of the file. Because the assumption is that it's in the folder that matches the name of the project. Because if you open one of these project files, and it's not in a folder named the same thing as the root folder, it comes up with a warning saying it's going to make a folder and move the file you just opened into the folder. Like, that's how up the butt it is about that being the way that it needs to be. Right. And that's the thing, Thunder. In other languages, you can do that. But for some reason, with the way this is set up, it has to live in the root folder, which, whatever, it's fine. All right, let's see where we're at here. Granted, I don't know everything about this IDE, so if there is a way, they didn't cover it, but I know that it did bark at me when I didn't have the file in the root folder, which is funny because it does give you the full path, so it is getting pathing information. It's not in that local directory though. That's a temp directory. I'm not sure. I mean, if there is a way to do it, I'm sure there's some additional code to structure it that way, but for all intents and purposes here, it has to live in the same folder. Okay. Yeah, no, that's totally fair. There probably is a way to do it, but for our intent and purposes, it has to live in the same folder. Okay, so we have to then create our bitmap pointers. So we're going to create an array of pointers to each of the bitmap images. So we're going to have landing underscore 1 through 4, and we're going to match the name of the bitmaps on the other side. Just for convenience's sake, we could call this whatever we want, but frankly, if it's a pointer that is literally pointing to something else, you might as well make it the same name, or something very similar, so you know what on earth you're looking for. And then by doing it this way, we're declaring this is an array of bitmaps. So within this variable called switch underscore bitmaps lives these 4 bitmaps, and we're declaring them all in the same area. And then we're going to do some includes to make the rest of the hardware work. That's our pins for our 7-segment display, and our include that makes it work. This is then our object that we use to indicate the hardware and the name of the object that we decide to come up with. In this case, it's bitmap underscore number underscore display is the name of the object we're going to use within our code that identifies this particular 7-segment display. Your project can have more than one of these displays, and the way you're going to identify them from each other is based on this name. Make the names make sense. Then it's easy to keep track of where you are in your own code. And that kind of runs off with it. And then we're going to define our pins for the dip switches. Let's see here, we will need almost all pins for day 29. So here we show that we can use analog pins as digital pins where necessary. Now, granted, we are on day 28, not day 29. That is not a typo. It's preparing us for what's to come the next go around. And then we're going to get to the part where we declare our keypad. Now, this is going to look a little different than it normally would, because we have column pins 10, 11, 12, and 13, and row pins 9, 8, 7, and 6. And that's interesting. They changed this back. Okay, so I was watching a little bit of this. Unless, does that change further down here? We initialized the whole keypad, but do we do anything different with it down here? Interesting. Okay, so if you watch the video where Alex takes you through the guided example, they don't declare the whole keypad. This 4th row is not included in the video. And that means that pins, or the declaration for 13 and 6, which are the last 2 pins that activate the 4th row of keys, isn't hooked up in the code. Physically it's connected, or you don't even have to connect it, but you can use a portion of the keypad without having to wire all of it. So if you did have a project and you had one of these 4x4 keypads, you could actually save yourself on wires by only wiring some of it, especially if you don't need all of it. I'm a little perplexed to see this here. I wonder if they changed it back after making the video because it was confusing by not including it, and then probably in day 29 then they include it. I don't know, we'll see. But yeah, I'm surprised to see that there, but all right, cool. So now that we have that figured out, we then have our keypad, which I love. This is called My Awesome Pad. Love that. That's kind of silly. We then we pass it the button map, which we feed it the rows and the columns, and then the numbers that make up where the pins are connected. So these are not random numbers. These are where I physically plug them in on the board. So that's digital pin 11, 10, 12, and 13, and then 9, 8, 7, and 6. This down here is our meaning for the button, because we have 16 buttons in total that are here. And if we don't declare what the button means in the code, then clicking it will activate, but nothing will pass because we didn't tell it what that button press means. by giving it a meaning, whether that be a letter or a number or a symbol, is what allows us to actually take action on that click after we do so. These can be whatever you want them to be. They're declared as chars, which means they have to be individual characters. But in theory, you could define this as something more complex, like a long or an int or even a string. But generally speaking, to keep the code compact and clean, a lot of the examples, at least I've run into, these are just individual chars. And this is a pretty standard keyboard layout for a general keypad. So we're going to just leave that the same as it is. Okay, so next we're going to jump into here is our enumerators, which is going to allow us to switch between, which allows us to detect the different states that we're in and give meaning to them. These absolutely could be anything. We could call them anything, but this is giving us meaning in our own code to what this is actually going to be for, right? So we have our approach initialization, which is abbreviated as INT. It says it ensures all the switches are off to begin. Our pre-flight indicates that all of our switches were in the off position, and now we're ready to move forward with the ability to lower or raise the landing gear, and then a final approach is actually doing the move. Now there's some stuff commented out here, but that means that this is probably in relationship to day 29 that we haven't done yet. Okay, so to be able to detect what state our landing gear is in, we can give that some basic values here. So we could say the gear bitmap count is equal to however many bitmaps we have and divide it by, well, that's actually not directly related. Yeah, this down here was what I just started talking about. Our gear, whether it's sitting chill, either deployed or not deployed, is a 0. And then if we're moving in a lowered position, we're 1. Well, we want to go back to idle, which means we're collapsed. Then that means -1. You subtract 1 from 1, you get 0. Which gets us back to idle, which is the collapsed, condensed version of the landing gear. But to figure out how many frames that we have in our animation, that's what this thing is right here. By taking to figure out our count, which is an integer, because there can only be whole numbers in the amount of bitmaps we have. You can't have a portion of a bitmap. We're going to get the size of the variable switch underscore bitmaps and divide it by the size of the very first bitmap, which is in position 0. That's a bit of a weird way to go about that, but fair. Size of the bitmaps divided by the size of, I don't know, I'm a little confused as to why we're dividing by the size of it if we already can just It's supposed to be a simple mathematical computation to figure that out. I'm just not sure why we do it that way. But as all things go, from here, we do activate the serial connection between the developmental board and the computer that we're on. But from what I saw in the video, this isn't used. So I'm not going to bother opening up the terminal because there's not going to be any input to the terminal. But we do start this connection. But the reality is, as long as I had power to the developmental board, this should work just fine even without the computer being connected. And we're not getting any input or output sent to and from the computer. So this is kind of unneeded, but it's here for giggles, I suppose. And then we do a little setup. We will clear our 7-segment display, set it to maximum brightness. And then we're going to dictate our pin mode. So we have our confirmation lever, systems, and thrusters. We're going to set those to inputs, because detecting whether the switch is on or off, we're sending data into the board, not controlling an LED, which would be sending information out, right? Blinking an LED is an output, but reading the state of a switch, that's an input. So that's why it's listed as an input. And these can only ever be in the state of input or output when it comes to working with connected hardware for the operation mode of the pin. Alrighty, and then from there, we go ahead and set the basic parameters for our OLED display. So we're going to initialize the display. Now that doesn't actually mean that that doesn't mean we're going to show anything on the display immediately. Hello there. What do you go by? I see a combination of things here. But yes, thank you for the follow. I would appreciate an enunciation of how to say your name, because I don't think I'm gonna get it right, and I'm not looking to insult you out of the gate by butchering your name, if I can help it anyway. Okay, now something we haven't done in the past, but we're gonna do this time, is set the font. The font is what the text looks like amid all of the I lost my train of thought there. This is what the text is actually going to look like on the display. There's a lot of different types of font one can choose, and it's something that just a lot of different options. And even if it does, we don't have the font we want within this library, you can import other fonts and then just call them in your project. So you can have a lot of fun with this. Now obviously it's a very, very small display, right? So the bigger the display, the fancier you can get with that kind of thing, but nor here nor there. And then we then have to set the reference height of the text. Now, two things have to happen here. We need to know how tall our text is, and then we're going to draw from the top down. Because if we drew from the bottom up and the top of our text, like say a capital T is taller than a lowercase t, because it is, that's almost always the case in most fonts, we don't want it to get cut off on the top of the display. So we're going to figure out where the center of our display is, we're going to figure out the highest portion of our text, and then draw that respectfully on the display while still being able to see everything. And then we figure out our coordinate of our tallest character. That's very important. Now that does change throughout the course of the code. So this is something that happens in our setup phase, but it somehow stays relevant throughout the rest of the code. Actually, think about it. Technically, no, it doesn't actually change because the bitmaps are always the same size, and the text that we're providing in this example actually is static. Okay, no, that actually makes sense. Let's see when we get a little further down here. All right, so we've got static integer current gear bitmap is equal to 0. Start with image of the lander with the gear in the up position. So we are going to declare that, and then here are the states of our code. We'll run through. We'll build this later to perform the actual approach, flight, and landing in the mothership bay. So that's a little bit of a note indicating that a little bit more happens later on in the next exercise. Now our approach state should point to approach.init. So let's go find that. That should be down here somewhere. Oh, there you go. It's right here. Hey, Jetron, welcome on in. Now, what we could see here is that we've got the state of our gear, our landing gear. Now, last key is just automatically set to a -1. Key previously seen. Now, that's just manually set there at the top of the code, which is a little strange. Now, this is at the top of the loop, which means every time the loop iterates, this is a static thing. This does not change. And then we have our 3 switches, and then we tie them to which respective pin they're plugged into. We've done this before. And then we're going to go through some switching statements. I have been waiting a long time for there to be switching statements in this kind of code, because we've done a lot of stuff that has been if else, and then eventually else. We haven't done a true switching statement in a sense, like I kind of anticipating we'd see sooner. Why does one use a switching statement over if else statements? Well, an if else statement is look at this case, and if it's not, go to the next one. And then you do another computation, and then keep working your way through all the if else, then do this. If and not, try this, and then try this, and then try this. And then eventually you get to the bottom, or you lose your mind. One combination of the two. With a switching statement, you have the different cases that will then call. So if our approach state is in the case of approach initialization, or INT, we'll then run this code and then break out of the switching statement. So that means the loop ends and you go back to the top, or run any code that's below the switching statement and then cycle back to the top. That's where these come in handy. So we have our initialization, pre-flight, and then the actual approach final. And then we're going to look at these because we have a completely separate switching statement below that one. Now we already know from what we saw is that if we believe our approach is in the initialization, then that means our thrusting lever, systems, and confirmation lever are all not true, which should mean that they're all off. And then our approach state is then manually set, thanks to this, into our pre-flight. So everything is off, pre-flight ready. We then go into the case in the next loop of the pre-flight. Well, now our case matches that. So then what do we do next? We then need to check and see if our levers are then all turned on together. It doesn't care if they're turned on one at a time or if it's just one combination of the two. It's just making sure all 3 are engaged. Once that happens, then we go to our final approach. Our final approach then puts us in the position of capturing the button press from our keypad. The myAwesome keypad is the object that we declared, and then .getKey is the function that actually waits for us to click something on that keypad. To which then it says if the custom key, which is the button press we have, and the custom key is not the last key, which if we take a look at what's up here, you'll notice that the last key at the beginning of each loop is a -1. Now, if we scroll up a little bit here and look at the actual keypad options, there is no -1 option here, which means that we're setting the keypad press to something that just isn't on the keypad, which then indicates that we couldn't have pressed it. It can't be the same thing. Statement not true because of the exclamation mark. You still remember exactly that is exactly what that's about. The exclamation mark is the reverse logic. Now I'm gonna be completely honest with you. When I write stuff when it comes to Boolean statements, I try my best to stay away from the reverse logic things. Unless it's absolutely necessary, I like to write things to look for the state when it's true, or indicate that If it's true, we're doing nothing, and then if it's false, then do all the stuff. But in their example here, we don't care if the switches were all in the true true state. We want them to all be off. So they just wrote it in a way that they only checked for if they were all off to be able to get out of this initialized state. But I'm gonna be honest with you, if I was writing this, I probably would have had a statement that just said if they're all true, you're not doing anything yet, else that means they're all off, and then go to town. But that's really just coding preference. Whatever makes it make sense in your own head. Because if it doesn't make sense to you, then future you is going to be pretty upset with past you. Which is why it's a little dangerous to copy and paste code like what I'm doing right here. I can identify this is not the way I would normally write this, but we're wandering through a guided exercise. If I was grabbing code from off the internet, would I change the logic around? Maybe, maybe not. It depends on how I feel about it and the way I feel like I write it. For me, I probably would have changed it, but I'm not looking to break it. We have a lot more to still go through. But just know that understand your own preference and make sure that you can, at a minimum, leave yourself some breadcrumbs or notes, in this case comments, in the code to indicate what it does. So then if you come across the code that you reused from somebody else, you have a clue of what it does. So you don't have to figure out the whole thing all over again when you revisit it in the future. Write your code and comments so that you can understand what happened in the past. This is no different. I've said that on several occasions, and I'm going to say more words in that same regard, because it's true. All right, so we now have that here. The custom key means that we're going to get, it has to not be -1, which it can't be, as long as that's the point. Right, you could do all these things with if-else loops too. Exactly, you absolutely could, which up until this point, that's how all the other exercises were guided. But they use switching statements. And to be honest with you, I kind of prefer the structure of a switching statement because it's all broken into labels, which are easy to track. At least in my head, they're easy to track because you've given meaning to it. You can still read through if-else statements, but you have to actually, look through it and understand what it's saying instead of just looking at a label saying like, oh, is the gear up? Well, let's see, does it fit in that bucket or not? And then, oh, okay, so it looks like we do in fact okay, so we do actually use the terminal. As I mentioned up at the top of the code that there was the serial monitor, it actually does print it to the terminal. So all right, I will turn the terminal on because it looks like we are actually in fact using it. And then our last key press is going to then be equal to our custom key press. So at the very beginning of the loop, it sets it to -1. And then here, it's then set to what we just clicked, which, okay, fine. We haven't made it back to the top of the code yet. The cycle is not over yet. So do keep that in mind. This last key is accessible in the scope of the main loop. Which means any of the code that's inside of the void main, this will be directly accessible to. If we have any functions that are written outside of the main block of code, like the void setup, this wouldn't be visible because it doesn't have the scope. It's out of scope. And what that means in general terms is if your house had walls, right? You're not in a studio apartment. You have a bedroom and you have a kitchen, right? The main loop is the bedroom and the kitchen is the initialization. That's the startup. If I'm standing in the bedroom with the door shut, I can't see any of the variables that are in the kitchen, and vice versa. If I'm standing in the kitchen and I'm looking at the closed bedroom door, I can't see any of the variables in there. I don't know what they contain because they're physically separated by that scope. Now there is the concept of global variables, which are visible throughout anywhere of the code, but that's the concept of local scope. It's what you can see within the container that you're working out of, which is important because this variable is very much visible by the rest of this loop. Now, what we then do is go into a completely separate switching statement. Now, the one we have up here, there's these breaks. You'll see after every case, which means that if the switches aren't all in the initialization state or the init state, then we break here and we don't check the rest of these. We ignore all that stuff. We then come down here, and because we were initialized and we didn't actually capture a key press, it's going to be equal to a -1, which means neither of these will be true. So that loop is ignored. We cycle through what's left of the code here and then shoot back to the top. Because we actually captured a key press by being in the final approach, we then check simply to see if the gear is raised or lowered, or if we're going to raise it. So we're going to use the case A and case B. Those are the two buttons. Now if we take a look at our little diagram up here, that means that the two most right buttons, upper right hand corner and then directly below it, these are the two buttons we are actually going to be using today, and the rest of the keypad is going to be unmapped. It's available for us to code it to do something, but for right now they're just buttons. They're just chilling out. And then from there, we simply, once we've clicked the key, then we just need to see, well, was that key one of the ones that matches something we want to do? If I click one of those other ones and I pass a 1 or a C or a D as in dog, then these don't match and nothing happens. The button still gets recorded, it still gets passed through the code, but if it doesn't match something that we've written for it to do something, well, then nothing happens. It still captures it and it passes it, but if we don't write it to do something, nothing happens. So if we take a look at case A, that says here, lower the landing gear unless it's already down. So then we take our current gear bitmap, and if it's not equal to the bitmap count -1, then we are going to lower the gear. We're going to lower the landing gear. So the gear state will be gear lowering. We break. We don't go to case B at this point then, because we haven't clicked that. We skip over case B, and then we head over here to some math. So we have the current gear bitmap plus the gear state. And then from there, we do another comparison to see if the current gear bitmap is equal to 0. We're not setting it to 0, we're checking to see if it already is 0. That's what the double equal means. Or, because of the double pipe symbol, the current bitmap is equal to the gear bitmap count, so there's a total of 4 in our count, -1. And then the gear state is set back to idle. We do see some stuff here that is going to happen in the terminal, which again is why looks like the video that they put together that describes what happens with the code, they changed after that video was produced. So I shot myself in the foot here a little bit by watching the video and not checking over the code, but hey, I get both sides of the coin here. We then indicate to the terminal the gear, and then we write out serial print line the current gear bitmap. Display the calculated switch value on our 4-digit display, which is going to tell us which of the 4 bitmaps we're going to be using. And then it looks like, I'm assuming further down, we're actually going to display said bitmap. I do want to point out that case B, which is the other button, is just raising the gear, which then indicates that if the current gear bitmap is not equal to 0, because 0 is idle, then we want to raise it. So that allows us to either put it down or stand it back up using those two buttons. I'm a little surprised we didn't just tie it to the same button, because you would think that if the gear's down, then the only other state I would want the gear in, it would be to be up, which if I click the same button the second time and I kept track of which state the gear was already in, well then realistically speaking, you would think you just use one button. But in this case, we're using 2, which is fine. Just another way it could be done. If you didn't have the extra hardware or the space to have 2 buttons in your project, well then, there you go. You save some space. And then here, let's see, we got some looping action. So we're going to go into this thing called a do while. So we're going to do all this code while this is true. So while, let's see, we're going to switch through our approach states. If we're in the initialization state, we're going to do nothing. Nothing happens. If we're in pre-flight, then what we're going to do is we're going to show on the display our states. So we have the approach state, the thruster level, systems lever, and confirmation lever, which I'm assuming pre-flight display. Oh, what am I doing down here? if things could not lose track of that, yeah. Whoop. Aha. I returned. There we go. All right, so yeah, our pre-flight display, we're going to load those things into it, and then that breaks, assuming that there's something in next page. So if I'm reading this correctly, what happens is that if there's multiple frames to the animation, we show all the ones and then flip through all the pages and refreshes until we've run out of things to show, and then it stops. If we're on the final approach, then we display our current gear bitmap, and then we end. There's a brief delay here of 100 milliseconds, which is a full second, so that we have an opportunity to see what's on the display with our faces. If that's not there, it would go through very quick, and it may refresh too fast for us to even watch it happen. So that's what that's about. There's a little bit of a delay there. All right, so then now we have a whole function called the pre-flight display. Now we could see up here that we passed these values into this void function. A void function indicates code that runs that doesn't return anything back to the main function. So by feeding it this information, we can then use it in the scope of this function. Now, as I had mentioned a little bit about scope, this curly brace right here on line 254, right there where the little red dot is the end of the main loop. This is a function that lives outside of the main, so it can't see anything that happened in the main loop. It just simply exists there, and we can call upon it when we need it. And we can call it that block of code as many times as we need it. We can then see here that an integer we're declaring as the current gear bitmap is a variable that we're declaring at the top of this function, and then we fed it everything else. Oh, I scrolled down too far. Sorry about that. The pre-flight display, this is everything that we have fed into it, and then here is where we actually store that stuff that we passed along. So it gets stored in the same order it's set down. So we have the approach state. So we have the ENU data class, and then we send it the approach state, and then we just called it the same thing. And then the Boolean that is the positioning of our three switches. We then do a little bit of voodoo math here that takes up the rest of our display. Now, I briefly mentioned over here that we're not using the whole display. We're using a portion of it because this code is going to use the upper portion of our display, and then our bitmap should be below it. We are then going to figure out our offset. We'll write our exploratory lander, and then we'll do some math to figure out our offset to right below it, our approach sequence. Set the Y offset to 0.4 lines above the bottom of the display. So then we're going to use this to draw some lines. And then we've seen this before, to set the text next to the three positions of our switches. And we want them to either say that they're on or off based on being true or false. And then clearing that line. So that allows us to draw all that on the display based on the position of our switches. And then our final display should be our current bitmap. Flash the lander bitmap if gear isn't down. Display the current gear bitmap as the gear lowers. So there's 4 frames that make up the gear, and it should wander through them all. The draw X bitmap displays each bitmap centered in the display base on its size. Right, now I'm curious to see how that's actually going to look on the display. Oh, there you go. Calculate our X and Y offsets for our bitmap graphics. So that's actually the code right there that figures out where to stick it so that it's underneath the other text that we're going to have. And then we have some stuff here. Helper function that returns a different string for each enumerated state. Liftoff state to string. Oh, okay. So what this is doing, so this is one of those functions that actually returns something. We feed into it our approach state that we figured out up in the top, which we currently have the initialization, pre-flight, or the liftoff, which looks like we don't have here. This stuff's grayed out, so I'm assuming that comes later. And then we just return which text we want to have appear on the display. So we have the init or the pre-flight based on our name of our variable, because we can't just tell it to draw the name of the variable. We called it that for easy like visual reference, but to actually have the text written out so that we could just take the block of words and pass it to the screen, that's what it's doing. And then last but not least, we have our draw string function, which should help us draw the words. Draw a line of text on our OLED display at XY, returning new Y values that is immediately below the new line of text. So this should just position everything we want to see in a fancy enough fashion, if everything goes according to plan. That is everything for today's exercise in a nutshell. I'm going to make sure that validates. And then we're going to switch to the bench camera. I'm going to click upload.
Okay, so I'm going to zoom the camera in a little bit here so we can actually see what's going on in the grand scheme of things. All right, so we can see here that our exploration lander then has the approach sequence, the position of our switches, and then the state we're in, which we're in pre-flight right now because all the switches were off when the code initialized. If I turn one of these switches on and then restart the code by clicking the little refresh button, the countdown is now in the initialized state because the thrusters are on, but the systems and confirmation is off. So to get it into the ready state, we turn all the switches off to get us ourselves into pre-flight. And then we can turn these on one at a time, where we turn on the thrusters, the systems, and then confirmation. Now I can admit I'm a little confused because I didn't click anything on the keypad yet. Oh, shoot. Okay, that explains that. I didn't realize, So I haven't actually tried this yet to see what it was actually going to look like. Now, I did just retract the landing gear. Let me turn one of the switches off to see what happens here. Interesting. Okay. So by resetting those, I can't get back out. I'm actually trapped in here in the moment. So I actually hit the reset button on the board, which will reset the state, put us back into pre-flight. I'm going to be honest, I didn't know what it was going to look like. That's really cool. So flip them all on, that then puts us, and then by clicking our two buttons here, we have landing gear down and landing gear up. And that's just clicking these two buttons that I have right here. That's switch 4 and switch 8 that makes the animation actually happen. And since it's 4 separate bitmaps, it's cycling through 4 different frames to make that look animated. For those that are artsy in the audience will completely understand that if you make animations, there's a bunch of little drawings that make up the pretty picture. And this is no different.
So isn't that interesting? That it's cool to actually see it in action. After everything we've done with it. Now, I'm a little confused, a tad bit here, by their wording, because they had mentioned in the very beginning of all this that there is going to be a need for the buzzer. Right? Now, I think they kind of confused their own exercises. 24 frames per second in animation. We got 4. Yeah, you got that right. You know, ironically, it's actually pretty smooth for what it is. They talked about the need for the passive buzzer, but it's not anywhere here. I'm sure that day 29 actually does initialize that, because it did say in the comments of the code that we're going to need all of our digital pins, or just about all of our pins on our hero board for the day 29, which is landing gear part 2, which I'm assuming then allows us to do different things with our buttons, which is just going to unlock a little bit more code. But we're going to hold off on that. I'm just a little confused as to why they mentioned it here, but like she mentioned it in a way that it sounded like we were going to use it, but it's not down here. So the pacing's a little confusing on the video that makes up this, but it's cool to actually see the animation. I have to admit, I'm a little bummed that out of all the time I've spent, I haven't been able to successfully make a bitmap to put on the display. And also, the bitmap itself didn't take up, it took up the whole display, but it was in a resolution smaller than the whole display. Like it didn't need the whole workspace, but it took up the whole thing because all the text was hidden when the graphics showed up. It's not a big deal, but it just it equates to a very interesting looking exercise, I guess, in that regard. I don't know. This one just leaves me a little confused. I realized that it's broken into 2 pieces. So yeah, what we're gonna do though for the next iteration where we do the 30 days lost in space, I'll double check and see if part 2 is enough for it to be its own thing, or if we're just gonna wrap up day 29 part 2 and 30 and like just do it all in one stream. I gotta check and see what the angle is here, because I'm a little confused as to why they broke it up, and I really don't, I'm sorry, I don't really have the time to jump into it tonight. Wait, I'm actually confused here. Wait, what? Oh, it's called Landing Gear Part 2 Day 29. Yeah, I don't know. I really don't think Day 29 is going to end up being enough by itself to really be what it is unless they add a lot of additionalness to this. I don't know, we'll see. If it's a lot of the same code, we might just gloss over a lot of the same stuff, because I don't have a reason to go through all of the same stuff if we just change a couple lines of code. We'll see. Yeah, that's probably what it's gonna be, which is fine, but it something tells me that for the next 30 days in space, we're probably gonna combine the last 2 days.